All right, let's talk about graphics in the media. Okay, so beyond the basics, we've talked about graphs before, we've talked about bar charts, we've talked about pie charts. Now let's talk about multiple bar graphs. Okay, so these graphs have two or more sets of bars that allow comparison between two or more data sets. All the data sets must have the same categories so that you can be displayed on the same graph. So make an apples to apples comparison too. In cases in which the data categories are quantitative, a multiple line chart can also be a better choice. Okay, and then we're going to talk about stack plot. It shows the different data sets stacked upon one another, and data can be stacked in both bar charts and in line charts, as you're going to see. Okay, so here is a multiple bar graph. So this compares men and women in as far as degrees go. Okay, and so each of these bars represent the median annual earnings. For full-time workers ages 25 and up, and this is by the educational attainment by educational attainment and gender. Okay, so here's on the x-axis, you've got it split. So these are horizontal bars, right? So you can have a horizontal bar chart, and that's totally fine. They could have done it vertically too, right? So in this case, maybe it made sense to have everything going off to the side with the length of the names, right? But again, it's fine. So you've got the degrees, the educational attainment, the degree on the vertical axis, and then you've got the median income or earnings, I should say, annual earnings on the horizontal axis. And then you've got your legend here, right, for men and women, right? So you know which bar is which. And so you can compare based on degree. You can compare males and females by degree. Okay. Also, here's a sample line graph. So again, you've got each line represents a degree, right? And then the horizontal axis, the x-axis is year, it's time, and then your vertical axis is the unemployment rate. Okay, so you can see how the unemployment rate has changed over time for each for the group that has each of these degrees, right? And so you can see similarities between the two, the different trends. They seem to be parallel for the most part. But you can also see that the higher the degree, the lower the unemployment rate seems to be. Okay, so you can definitely make comparisons. So example one, education pays. So what general messages are revealed by the graphs of the previous two slides? Let's comment on how the use of the multiple bars and line graphs helps convey these messages. Okay, so let's go through these. The bar graph conveys two clear messages. One, people with greater education have significantly higher median incomes. Okay, that's definitely shown. And then for equivalent levels of educational attainment, women still earn much less than men. That's what we see too. Okay, so the other part is no matter what the unemployment rate is, at least over the time period, unemployment has always been significantly lower for more highly educated people. All right, a stack plot. Here it is. So here's an example of a stack plot. So you've got expenses, right, for college. And so to compare the different types of colleges, right, so public 2-year commuter versus a public 4-year in-state on-campus student versus a public 4-year out-of-state on-campus student versus a private non-for-profit 4-year on-campus. Okay, so and then you've got the breakdown for the costs right down here. And so you can compare the different costs for the different types of schools that one can attend. Okay, and you can see where your money is going for each one. Okay, Here's another type of graph. Okay, this one is on the causes of death. So these are your vital statistics, right? So these use four causes of death: pneumonia, cardiovascular, tuberculosis, and cancer, right? So then you've got the death rates here on the y-axis, the vertical axis, deaths per 100,000. And then, of course, this is a time series. It's over the course of years. Okay, so these are trends. Notice it's got a nice title. It's got the trends and death rates for the four serious diseases. Okay, 1900 to 2011. Okay, and it says, what was the death rate for cardiovascular disease in 1980? Okay, so in 1980, the rate would be based on the green, right? So you would measure the distance from the top and the bottom, and that would give you your death rate. So for 1980, the top of the cardiovascular wedge is about 620, while the bottom is 180. So you'd subtract those two, and you would get a death rate of approximately 440 deaths per 100,000. Okay, so that's how you would calculate the different death rates on a graph like this, where the areas are stacked on top of each other. Okay, so that's what we just discussed. And it says the downward slope of the top wedge shows that the overall death rate for these four diseases has decreased substantially from 800 deaths per 100,000 in 1900 to about 434 deaths per 100,000 in 2011. Okay, so it has gone down significantly. The gradual disappearance of tuberculosis wedge shows that this disease was once a major killer, but has nearly been wiped out. Okay, the widening and then narrowing of the cardiovascular wedge shows that the death rate for the disease grew in the first few decades shown, but has declined in recent years. And the cancer wedge shows that the cancer deaths rates rose steadily until the mid-1990s, but has dropped somewhat since then. Okay, now, graphs of geographical data. Okay, so this is going to give you a couple of other types of graphs that we can look at that are a little different than what we have shown so far. Okay, so these are going to be different types of maps, right? So for example, here we go. So we've got the map of the United States, and we've got the energy usage, right, for each state. And so we've also got a legend here that tells you basically what bucket each state will land in based on the color. Okay? So the darker the color, it seems, right? Blue and green use the most energy, where the orange and yellow use the least. Okay, and these are equivalents, these are energy use and equivalents of units are gallons of oil. Okay, gallons of oil. Okay, so this would be a way of displaying graphical data that you can look at and see, okay, which states use more or less energy than other states. So you can quickly get a comparison. You can see trends across the regions, right? And here's a contour map. Now this contour map deals with temperature. So you can see the gradation of temperature from the northern part all the way down to the southern, right? So you can see as you get closer and closer to the equator, the temperatures rise. And so that makes sense, right? And you can see that widely separated contours mean large regions have nearly the same temperature, like in here, right? Okay. Closely packed contours means that there are temperature differences over short distances, right? Like over here, right? So if you travel from northern Illinois down to southern Illinois, you'll see a change in temperature. Okay? Whereas pretty much Mississippi and Tennessee pretty much have the same temperature. Same way with Iowa and yeah, pretty much Iowa. Okay. Now, let's use the figures to answer some questions. So, what geographical characteristics are common to states with the lowest usage per person? So those would be the orange, right? Orange and yellow states. So the color coding shows that the states with the lowest category of energy use per person are all either warm weather states that we saw with California, Arizona, Florida, and Hawaii, or they're states that are more densely populated regions, as in New York, New Hampshire, Connecticut, and so on. Okay? So that's a takeaway. Now, were there any temperatures above 80 degrees Fahrenheit in the United States on the date shown in the contour map? If so, where? Well, yes, because we saw the red, right? The red is 80. So we've got over here in Florida. Okay. Now, the only other place was over here, but that's in Mexico. Okay. Now, let's talk about three-dimensional graphics. Okay, so now, with computers and software, it makes it really easy to make three-dimensional graphs and all kind of really nice looking and, you know, graphs and stuff, but really, you want to stay away from three-dimensional graphs, okay? It says computer software makes it easy to give almost any graph a three-dimensional appearance, okay? Allow us to show richer data sets, okay? However, can be difficult to read the data precisely. Three-dimensional graphics, therefore, tend to work best when they are interactive online so that the figures can be rotated, viewed. So yes, if you're able to turn the graph and look at it from different angles, then yeah, that would be great. That would be great. But in most cases, when you're dealing with 3D graphs, it's a 3D graph on a two-dimensional space, which is very hard to interpret. So I recommend staying away from 3D graphs. Stay with two-dimensional graphs when you are printing something, or if you're displaying something on a PowerPoint. Okay. For example, here, this is a graph that is really busy. There's a lot going on here, and it's tough to see where to compare, especially like here, right? It's because it's not necessarily, it may not necessarily be obvious that the light blue bars are taller than the purple bars, okay? Because again, there's a depth to this that you have to consider. I mean, what about which one's bigger here? Okay, I'm not 100% sure. Or what about these two, right? The purple and the dark blue, okay? Or what about this one? Are they the same? Is the purple smaller or larger? It's vague. It's confusing, okay? So you want to be aware of that, okay? So it says, based on figure, about when did China surpass Russia in total carbon dioxide emissions? Okay, so basically, so we've got China and Russia. So China's the yellow, okay, and Russia is the light blue. And so I would say that China surpassed Russian total carbon dioxide emissions between 1990 and 1995 is what I'm guessing. Yeah. Now, there's a few questions about graphics that I absolutely strongly exhort you to stay away from. Okay, so perceptual distortions. Many graphics are drawn in a way that distorts the perception of them. Watch the scales. Okay, so make sure that the scales are correct because they can be visually deceptive as well. And then percent change graphs. Graphs that show percentage change can be misleading unless they interpreted with great care. And then pictographs. Stay away from pictographs. Don't use them. So here's an example of perceptual distortion. This is a pictograph, right? It's showing the decline of the dollar, the buying power of the dollar as it's declined over time. So 1980 to 1990 to 2000. Okay, the years are not equally spaced, right? So here you go 10 years, right? And then here you go 15 years. And then of course the dollar, right? This is a dollar in 1980 is worth 63 cents in 1990. But look at the dollar though. The dollar is less than half the area of the original dollar, which gives you a different view, right? Okay, because 63 cents is 63% of a dollar, right? So again, in here, now it's gone down to 42 cents, but 42 cents is closer to 63 cents. But look at the dollar. This dollar here is less than half the size of this dollar. So it just perceptual distortion, right? Because our eyes focus on the area. Okay, so be careful. Now here's different vertical scales. So whenever you have a vertical scale, you want to start at 0. Always start at 0 because it can give a distorted view when you don't start at 0. So for example, in these two graphs, we see that there's a much stark difference in the first graph with the blue line because you start at 0. So all the peaks and valleys are much more pronounced than in the other graph with the red line where you do start at 0. So it's actually not as volatile as it appears to be in the first graph. So this is one of the reasons why you want to start at 0 whenever possible. And if you can't start at 0, always put a break in the graph to let your audience know that, hey, there's a break in the graph here. And usually that's done because to make the graph fit on the page, right? So we do that, okay? But in that case, we still always start at 0. There's just a break in the graph. Let's see here. Here we go. Here's another one, different horizontal scales, right? So we're looking at world population here. So we're looking at billions of people, right? So if you look at this graph, it gives you the perception that the world population is growing linearly, right? But the reason why it's giving that perception is because if you look at the years are not uniformly going up by a uniform increment. So if you look at the time between 1804 and 1927, you've got the span of over 100 years. Okay, but then if you go from 1927 to 1960, well, now you've got 33 years, right? And then if you go to 1960 to 1974, you've got 14 years. So the gap between the dates, the years, is getting smaller, right? Okay, and so this gives the perception that the world population is growing linearly when in fact it's growing more of an exponential growth curve. And we'll talk more about growth curves later, but the purpose of this is just showing you that, hey, this could lead people to believe that there's a linear growth for a world population when there really isn't. Okay. All right, there you go. That is it for this section. I hope you had a great time. And again, please make sure you do your due diligence, use the resources, and hey, reach out for help either with me or with the Tutoring Center. And use the tools available in my math lab. They are wonderful tools that will help you. Okay, take care and have a great day.